Dear students, welcome to this session. In this session, we will talk about how to derive the computational formula for degree of freedom of a mechanism. Now, before jumping to the derivation, let us talk about a planar mechanism. So, throughout the entire kinematics of machines course, we are going to consider a planar mechanism for analysis. So, a planar mechanism is defined as a mechanism in which all the links move in a single plane or in parallel planes. That is, it is possible to define the motion of all the points on the individual links in a mechanism by using a single plane only. So, now let us see how can we derive the formula for calculating the degree of freedom of a planar mechanism. Let us consider a mechanism where the total number of links is n. Now let us try to see that what will be the degree of freedom corresponding to the n number of links in a mechanism. We know that a link is a simply rigid body. Now for a rigid body in three-dimensional space, generally we have 6 degrees of freedoms. So let us see how. So if you see here, if we consider a cube in a three-dimensional Cartesian coordinate system, this cube, it can translate along the x, y in z directions, and at the same time this cube, it can rotate about x, y and z direction respectively. So the total degree of freedom for this cube, it will be equal to 6. Now since we are talking about a planar mechanism, let us move to a two-dimensional space. Now in a two-dimensional space, let's say we are restricting the motion of this cube to xz plane only. Now in a two-dimensional plane space, if you observe, the 3 degrees of freedom are arrested and only 3 degrees of freedom are allowed. That means now this cube or rigid body, it can translate along x direction, it can translate along z direction, and it can rotate about the y axis. Now let us see here. We know that the basic definition of a mechanism, it states that it's a closed kinematic chain where one of the link is fixed. So in this case, the total number of movable links in the mechanism, they will become equal to n minus 1. Now each of the link or a rigid body, it has 3 degrees of freedom associated with it. So the total degree of freedom of n minus 1 movable links, it will become equal to 3 multiplied by n minus 1. Now let's assume that J is the total number of simple lower pairs in the mechanism. So as soon as we introduce the kinematic pairs that are going to connect the different links in the mechanism, obviously certain degrees of freedom will be getting arrested. Let us see how. So when we say that J is equal to number of simple lower pairs, it simply indicates that a simple lower pair is nothing, a pair with degree of freedom equal to 1. So it could be either a simple prismatic pair or a simple revolute pair. Now we know that a prismatic pair, as we saw in the previous sections, it simply allows only 1 degrees of freedom, and the same is true for a revolute pair also, that also allows only 1 degrees of freedom. That means in case of a prismatic pair or a revolute pair, 2 degrees of freedom are getting arrested if we consider this revolute and prismatic pair as a part of a planar mechanism. Now since J is the total number of simple lower pairs in the mechanism and each lower pair, it is restricting 2 degrees of freedom, so the resultant degree of freedom, it will simply become equal to 3 n minus 1 minus 2j. let us again assume that H is equal to the number of higher pairs in a mechanism. So as we just saw in the previous sessions that a higher pair, it allows 2 degrees of freedom and it arrests 1 degree of freedom. So if each higher pair, it is restricting 1 degree of freedom and H is the total number of higher pairs in the mechanism, so the resultant degree of freedom, it will become equal to 3n-1 minus 2j minus h. This equation is popularly called as Kutzbach equation. Now, let us see one modification of Kutzbach criteria that is called as Grubler's criteria. So, a Grubler criteria is applicable to a mechanism whose degree of freedom is equal to 1. So, let us see how this entire equation it gets modified. So, we know that 3n-1 minus 2j minus h is equal to the degree of freedom of a planar mechanism. Now, if the degree of freedom of that mechanism it becomes equal to 1, so this equation it gets modified something like this: 3n-1 minus 2j equal to 1, and finally the resultant equation it becomes 3n-1 minus 2j minus 4 is equal to 0. So if any mechanism it satisfies this criteria, so that mechanism is called as a constrained mechanism. Now let us try to physically interpret the meaning of a constrained mechanism. So for that, let me just draw a mechanism which is consisting of 4 links only. So let us assume this link as fixed link, link 1, then this as link 2, this as link 3, and this as link 4. Now all these links, let us assume they are being connected by simple revolute pairs. Now when we say a mechanism is a constrained mechanism, that means, let's say if we rotate this link 2 through a certain angle theta, so the remaining links, link 3 and 4, they will also turn through certain definite angles. You can say this angles as beta and phi. That means there is a unique relationship between the motion of the input link and the motion of the remaining links in the mechanism. So you can say that beta it will be a function of theta, phi it can also be expressed in terms of theta only. Now let us understand, if this is a constrained mechanism, then what exactly is an unconstrained mechanism? In an unconstrained mechanism, there will be no unique relationship between the angles beta, phi and theta. So what does it mean? So let's say, let me again consider the same mechanism. Now let's say at any instant of time t1, I rotated this input link 2 through angle theta 1, and the output link it also rotated through angle phi 1. Now again let us consider at another time instant t2, right? I rotated this input link through angle theta 2 and the output link it get rotated through angle phi 2. Now here you can see that even if we provide the same rotation to the input link, that is, even if we make theta 1 equal to theta 2, we obtain 2 different values for the rotation of the output link. So one time we are obtaining a value phi 1, another time we are obtaining a value phi 2. So in such cases, the variable phi it can take any arbitrary value with the rotation of the input link theta. So that indicates that this mechanism is a unconstrained mechanism. So just remember, in a constrained mechanism, the motion of all the links it will be definite and distinct. Whether in an unconstrained mechanism, the motion of the links can be arbitrary. Now let us see some of other the important points to note down. So if the degree of freedom F is greater than 0, then we simply say that it results in a mechanism with F degrees of freedom. Now if we say that F is equal to 0, so this results in a statically determinate structure. Now what is a statically determinate structure? So a statically determinate structure, it simply means that a structure which is not possible to solve using the equilibrium equations of motion. Now what are equilibrium equations of motion? So equilibrium equations of motion, they are simply defined as sigma F vector is equal to 0. That means the summation of all the forces in the mechanism, it should be equal to 0. And then sigma M vector is equal to 0. That is the summation of all the moments in the mechanism, it should be equal to 0. Now if using these two equilibrium equations, it is possible to solve the structure, so that structure will be called as a statically determinate structure. Now if F is less than 0, then this mechanism, it will reduce to a statically indeterminate structure. So what is a statically indeterminate structure? A statically indeterminate structure, it simply means that these two equilibrium equations, that is sigma F vector is equal to 0 and sigma M vector equal to 0, they are not sufficient to solve the structure. So in this case, we need to generally invoke constitutive relationships that define the relationship between the forces acting on the links and their deformation. So, and at the same time, we also need to apply compatibility conditions in order to solve the structure. Now, with this, I would like to conclude this session and see you in the next session.